Okay, this is 3.1 steel connection design. Again, this is mostly AISC 360 connection design again, and some of them we do reference to other code, like when we do the welding code, a reference to the AWS D1.1, and when we do the bolt connections, we reference to the RCSC. So there's again, when like I say, the building code is the basic.
Yeah.
Once it goes there in reference to the AISC 360, and within AISC 360, they reference to specific documents for welding, for bolting, and for construction tolerances. So again, you have to drill down from one level to another just to get to the design of these connections. So steel connection design. Typically, you have a typical. We just cover the gravity load and wind load. I call this a typical design. And then after that, we have the seismic design for the connections, earthquake loads, capacity design. Capacity design and the design with omega loads are pretty similar. The capacity design concept, like I said before, is you have a ductile link, and then you design for that link for all your forces, the earthquake forces, and you make sure everything is stronger than that link.
Yeah.
So we've heard that many times. Chapter J of the AISC 360 is where the connection design is being referenced. However, there are also other documents by AISC that covers different moment frame topics. So like 13, it's on stiffening of the column flanges, basically on when you use the continuity plate or stiffener plate. Chapter 6, the number 16, is the end plate moment connection. So moment connection end plate. There is actually a design guide 4 that covers the same connection, but for seismic provisions. And I'll show you that later here. So anyway, so what we have here is 341. Once the building code references 340 or 360 or 341, then this is where you do your connection design. So when it comes to moment frame design, steel moment frame specifically, they go to 34105 and 341. However, 341 also covers other systems as well, not just the moment frame, but also brace frame, eccentric brace frame, buckling restraint brace frame. So all the steel ladle systems and steel shear walls as well is covered in the 341. So to be more specific, now that they introduced the 358, and these are the ones just on moment frames itself. That these have been pre-qualified ones. Like I say, the engineers could come here, use this document, select which connection they want to use. They don't have to do testing if they select it from this document. And what we keep saying is we want to get into this document. Simpson's trying to get into it. Our competitors trying to get into it. So engineers could actually just pick it out and design it themselves. And actually, that's part of the code.
Yeah.
So some of it already, the Kaiser bolted bracket is already in here. The Connextech is already in here. So there's the side plate, and us is trying to get into the next version and is currently under review by the AISC committee. So that's the status. Design Guide 4 is mainly for extended end plate connections. You could have stiffened or unstiffened, but that's mainly end plate connections for seismic and wind applications. So for our connection references, the first one is obviously a code report. Right now is draft. We'll be getting it by the end of the year. The draft wouldn't be here, so we would have the ESR. And within this code design procedure, we'll have the step-by-step, like I showed you guys in the previous slide. Step 1, design this. Step 2, design that, and blah, blah. So it's all actually included as part of the code report. This very much the same as what we have the code report and what will be our chapter in the 358. It also spells out different limitations and design requirements. These two documents for us is pretty much the same because we're basically applying to two different documents or agencies to get our approval. So either way, it doesn't matter which one we use, our result should be the same. I don't think we modify anything between the code report or between the AISC 350 submittal. In here, for us, we also reference back to the 360.05. Okay, most other people would reference the 341.05, and the reason is, remember, I keep telling the flange thickness ratio, B to T thickness ratio, needs to meet the 341.05 or 341.10. We reference some things, but we're minimum compared to your typical welded or bolted connections I showed you guys earlier, where all the hinging is in the beam. So or some of them they have in the tube beam, but most of them are in the beam, so they would have to meet those B over T ratios. For us, our B over T ratio is from the 360. That was the previous presentation. I say what we're going to highlight, but this is chapter J, is the designer connection from the 360. Okay, well, when you come to the 360, again, like I said, you have to drill down to the different design. When you have bolted connections, they reference a document which is called the RCSC, Specifications for Structural Joint Using High Strength Bolts. For welded connections, they reference the AWS D1.1 for welded steel. So what this one did is they actually took their requirements and put it in.
Yeah.
So, and make some exceptions to that. So which ones they want to adopt, which ones they don't want to adopt. So instead of like the code that you have to go to these books, you could actually design without these documents, but they reference them for obviously quality control, manufacturing, and other stuff that they reference them. But the design equations are actually all contained within 360. So like say for starting from J2 for welds, all provisions of the D1.1 apply under this specification except some of the following. What they're doing is they're modifying some of the sections in D1.1 and they're adopting some and not adopting some. So some of these are as excess hole geometry for one, filler weld effective area, PJP weld size, use of strength design instead of allowable stress design. So for the D1.1 is actually allowable stress design. They have not converted over to the RFD design. So essentially this code is saying use the strength design instead allowable stress design. Some fatigue stress design parameters are a little different, but we won't be covering any of these. This is for vibration, fatigue, or stress, or bridge design vehicles. A lot of loading cycles. Where your stress fatigue is concerned, we won't be touching that. Tubular structures, non-tubular structures, thickly loaded. There are some differences in design consideration. And lastly, the thermal cutting tolerance. I believe the AISC one is a little bit more stringent than the AWS D1.1. So when they cut, depends on what method they use, like smoothness, what we're talking about. They actually made it a little bit smoother than what the AWS requirements is. So in this code, just an overview, we won't be using it, but what it covers is a general requirement, design of welded connections. Most of these, as you can see, is related to welding pre-qualifications. So qualification, fabrication, inspection, stud welding, strength, and repair of existing structures. So all we're dealing with is probably design of connections. All this is for fabrication, for inspection, and everything else related to producing a good weld for the structure. So this is the different sections in the D1.1. In 3.1.1, the welding processes they cover. So to weld up a connection, they give you the strength, but also depends on what kind of welding procedure or process you use, and some of them could be different. Depends on which method you use, and I'll go over some of the advantages and disadvantages of each and show you what they are. So the first one is shielded middle arc welding. I think this one is probably most familiar with people. Is you actually have a stick. Yeah, you stick. You stick it in, and then you could go and weld whatever you want. It's very portable, very easy to use. The equipment is cheap, and you probably see a lot of actually countries, if they start welding it, they start doing this first. However, you do have what they call slack that's covering it, that they need to remove after each pass.
Yeah.
So what that means is you don't want to get that in your pool. And stick welding, it's The advantages are simple and cheap.
Yeah.
Cheap equipment, versatile, which you could take anywhere and you could do, not like you have to drag your machine around. Disadvantages, very slow. Imagine a semi-automatic, they don't have to even, after each stick, they have to take it out, replace, take it out, replace. The semi-automatic one just go and keep going until the spool runs out. So disadvantage is slow. You have to remove the slack after each pass. So if you guys know about welding, then that's one of the methods, and it is covered in D1.1. Okay, so another process is called flux core arc welding. There's two types. It's gas shielded and self shielded. So the gas shielded obviously uses a gas. You can see here blowing, and the gas comes in from the machine itself. Okay, this one is self shield. Self shield is basically is within the electrode, so you don't need the gas.
Yes.
So the gas, typically when you work outside, you have the wind and it blows the gas. It's not very good. So that's why sometimes they go with the self shielded. So advantages, very high deposition, which is where it means you could deposit a lot of weld, go quicker. Self shield can be used in the field. Okay, self shield, that's why I say don't have to worry about the wind. Disadvantages, same thing. Slack, both of them have a slack that they produce. And the equipment cost is a lot higher than just a stick. Another one, this one is called gas metal arc welding. Very, very similar to the flux core welding, arc welding with a gas. Okay, when you look at it, you couldn't tell the difference at all. But it depends on the different transfer modes that they have. See that this one's not even touching. So they have the short circuit, globular spray, and then post spray. Don't need to worry about that, but they just need different modes. And the AWS only qualifies a certain transfer mode. They don't qualify all of them when they say you could use it and without having to do a WPS. So advantages: high deposition rate, no slack, okay, no splatter almost, so you don't have to clean up. Complex equipment, advantage, very, very sensitive to wind, so you cannot do it outside, or environmental factors that the wind where is a big factor. Another one is submerged arc welding. This is actually what we're using to produce the OMF beam and columns. So when we have the plates together, you have one. They're using this method to produce the weld. So the weld comes out very, very nice and clean. However, because it's submerged, you cannot put it in any way. It has to be in the flat position. So they have to be in the flat position. High deposition rate, no smoke, lack of visibility of art. So for welders, they always put on a mask. They don't want to see the art stripe. This one, because of the cover, you don't really see it at all. So there's no visible. Disadvantages, obviously flat horizontal position only. You need to remove the slack, okay, and you have to keep the flux clean. This is the flux that they put on, or else it will affect the performance. One last one. This one don't use for structural welding, steel welding much, but a lot of aluminum. When you do the aluminum, this is called the gas tungsten arc welding. This is the tungsten electrode. This one do not melt like your other ones. Like your other one, when you go in and keep feeding through, this one do not melt. So you have to put in through a filler rod yourself, and this is what's melting. So that's gas tungsten. Very clean, very good for aluminum. You could weld very thin metal, no flux. Disadvantages. One high disadvantage is the worker needs to be very, very high skill, and then very slow.
Probably use a fly stick.
Yeah, you use a stick. So basically, they do that and add a stick and keep adding it. So this is called gas tungsten arc welding. Okay, so these are some of the summary, typically left to the contractor. Okay, we don't tell them what to do as an engineer.
Yeah.
We don't tell them what process to do, but sometimes we need to know if we're calculating the strength of their well.
Mm.
Well, this is the capacity we get for this procedure. This is the capacity we put in the procedure.
What time?
If we are using a capacity that's not typical and we want a specific procedure, then we need to indicate it on the drawings.
Yeah.
This procedure needs to be used. Okay, so that's what it is. A long, long, big, automatic. These are some of the best advantages. Gas is in the shop.
So what time we use? Yeah.
This one, I think this one was the flux core. The flux core self-shooted.
Yeah.
But I think this is what they use here. So, but again, typically this is left to the welding contractor. Okay. Joining plates. Okay, you have two plates coming together.
Yeah.
We call it a butt joint, a T joint when you have the two, a corner joint, and a lap joint.
Yeah.
Okay, that's joint type is different than weld type. Okay, weld type, you have the CJP weld. You see this the area of the plate and then the weld is the same size.
Yeah.
Versus the PJP, you only weld a portion of it, so you don't cover the whole thickness. You also have the filler weld for the T joints.
Yeah.
That's what this one is, the fillet weld. And when you overlap it, you could also either use a filler weld here, a filler weld on that side, or they use a plug weld to do both. And this is for very thin materials. They have machines that put stamp through and they weld it this way. So strength on the welded joint. Okay, so you know what the different types are now. What is the strength? So you, first of all, just the basic concept, you have to check it at the base metal, the base metal itself, and then you have to check the weld metal.
Yeah.
And typically, the weld metal is stronger than the base metal.
Yeah.
The weld metal is we're calling out for 70 ksi. This metal is 50 ksi.
Yeah.
So the weld metal is typically stronger, but obviously the AWE, the area of the weld metal, is
Small.
where you specify
Yeah.
is small compared to that. So that's why you have to check both the base metal and the weld metal, and all these phi factors, and then these are the stress or strain, stress, nominal stress of the weld metal or the base metal is given in table, and this is AISD 360 in table J2.5. Okay, when you go to table J2.5, they break it down into CJP, complete joint penetration weld. They give you a nominal stress, effective area, and then require filler metal strength level. Don't worry about this one, but these you need to look at. If you look at how they are loaded, they also based on the loading of the axis to the weld. Basically, for a CJP, we are utilizing the whole thickness of that section. Okay, the effective area, it is just the thickness times the width of the plate. That's for the weld metal calculation. Okay, this one is showing you the backing bar. This is what I was talking about last time when they have to remove the backing bar. Okay,
Yeah.
they typically have a root opening here, so they would fuse together. If you put it together like that, then at the bottom they don't fuse too well. So they typically need a gap between the two pieces when you weld it together. Okay, so that's for CJP. The effective area for the weld metal is essentially just the thickness times the whole metal itself. For PJP, is different. So you have to check the base, the weld, and then each one is with a different phi factor, and the nominal stress, FU or FY. So they tell you, spell it out here. And again, when you say effective area, they refer you to another section. Based on the they take you to another section. Okay. For PJP, you only get to use a certain area. You don't get to use the full area. So in that, the E is pretty important because that's what you welded.
Yeah.
A lot of in this project we don't use any PJP, but on a lot of drawings, if you look at the structural drawing, if they use the PJP, they would have to call out for how, yeah, what the well size, what's E that's required, the penetration exactly. So for the penetration, there is a minimum penetration, or there's a penetration that depends on the welding process. Like I said, you will need to know the welding process to determine what E would be. Okay, so that's why the welding process comes into play, and what that effective throw is, what E would be. Okay, so for most processes, R E equals S, so two are the same. But for these two, you will have to subtract 1/8.
Yeah. So that's why when we design the truss plate, when we cut it, we throw this 1/8 for the pole. Yeah. And when we cut the blade, steel blade, we trim as we have for like this, and yeah, it's the same.
Okay.
Yeah.
Yeah. So the truss plate, is this the bracket?
The knife.
Okay, the knife plate. Okay, so that's CJP, PJP. For J4, what to keep referencing to is the strength of the element in tension. When I said before, in tension, we don't worry about it for the member, but for the connection, it's critical, because that's most of the yielding, if they do, because you reduce the bolt hole, the plate by the hole size, or there's some path that might fail. So you have to check that in tension. That's the first thing probably they teach you in the university is you calculate which line of failure when you're pulling in, and that's what's important, to calculate the effective area. So the effective area and the shear. Okay, so ANV, the net area, AGV, gross area. So you have to check all these for your partial penetration. In addition, they give you a minimum effective throw that you have to use. Okay, you can't just from 1/4 inch to inclusive to smaller is your minimum throw you have to use is 1/8. So you can't be more smaller than 1/8. And then when you're doing a 1/2 inch, then you have to do a 1/4 inch minimum. So you can't go less than 1/4. So that's a minimum groove well requirement for J2.3. This is filler well now. Filler well is the failure of all the filler well if you look at it is in shear. Okay, so it doesn't matter if it's loaded which direction, it's in shear. So the base is J4. When we looked at previously, the well is now we're 60% of the FEXX, which is 70 KSI what we're using. And then the area, again, to kick you back to consider what area you're using for the well middle. So for the filler well, the terminology is this is the lake size. This is the effective throw. They take it at 45 to the lake size. Okay. For one that's symmetric, then the thickness is just basically 0.707 of the W. And that's based on geometry for symmetric lakes. Okay, so that's where the 0.707 come from when you're dealing with the welding. Is the effective throw and the lake size are not the same. For a linear group of wells of uniform size, you could actually increase the capacity based on the angle. So if you're looking at the angle at 0, your strength is, let's say they normalize it as 1. If you load it in 90 degrees, you actually get higher capacity. However, you're lower ductility. So there's a trade-off between higher strength and ductility in this equation.
The angle.
Yep, the angle of loading.
Of loading, yeah.
So typically, if you do it this way, it's 0, right?
Yeah.
So sometimes you could load it this way.
Yeah.
Or this way, that's where the angle starting to switch. So you get higher, you actually get higher capacity for pulling on it.
Yeah, pulling 9.
Yeah, for pulling this way, you get 90 degrees.
90
for that shear or this shear is the 0 degrees. So again, similar to the PJP well, for filler wells you have a minimum size. That's the numbers are very similar. For ½ an inch you need a 1/4 inch for the minimum filler size. So for our ½ an inch thick, the minimum without calculation is you have to do 1/4 inch. Okay, but 1/4 inch will not meet our strength requirements. Okay, so there's also a maximum size filler well as well. Most people don't concern this because the cases that occur is not very often. You don't want to weld it all the way to the top per se because you might burn this edge off. Okay, so that's 16 is typically what you keep. Also, when you're welding this kind of connection, the kind of like tension, the minimum size or the maximum size do not come into play. So like our OMF, there's the beam, there's the end plate. There is no maximum size where they're saying that doesn't apply because it's not burning anything off. You can see. Okay, bolt and threaded parts. So that was welding and welding strength. So you get basically 3 types of welds: CJP, PJP, and fillet. And the strengths are pretty straightforward in the design code. You check both the base metal and then you check the fillet metal for the strength, and then the minimum of the 2 strengths covered, and that's the capacity of your weld. For bolts, the reference is to the RCSC, the specification for structural joints using high strength, like I showed you before. Refer to RCSC specification. And here are the different chapters in the RCSC, similar to the AWS. Most of them are dealing with inspection, installation requirements. So installation, pre-installation verification, use of washers, joint type, bolt type, fastener components, blah blah blah. So all we worry about is the limit state in the joint. This is a strength calculation, and again, 360 has moved most of these equations into chapter J, so you don't really need to go back and refer to this one for typical cases. Fasteners, before rivets were used in existing structures. Now bolts are very common. So A307, A325. This is considered a common bolt. Ordinary high strength bolts are the A325 and A490, and that's what the AISC or the RCSC book covers. It's just the high strength bolts. For a bolted part, okay, I'll have it. I'll bring some in from a desk tomorrow. I have a whole bunch sitting there. You have the head, the hole from underneath the head to the end. It's the length. So when you order a bolt, you say 3-inch bolt. This is the 3-inch length that you're getting. Okay, the diameter is the diameter. So when you say 5/8 or 7/8 inch, this is the diameter by 3 inch, and that's the length you measure. Okay, threads is basically the threads. You know what it is for. So when you put the nut on, the grip is wherever the 2 plates coming together. How much spacing between your washer face and then the bottom of the nut, bottom of the head is your grip.
The thickness of
yeah, so when the 2 plates together, you're gripping it together. They call that the grip. There's a washer here, and then a nut. The washers are typically required for when you're pre-tensioning any kind of connection.
Yeah.
Their uses is because the area of the head, you might be digging into the steel a little bit, so they're trying to spread out a load. That's why the washers are there for you, so you don't dig into the soft material or just a smaller area. So that you use the washers. That's why there's a chapter in the RCSC. When do you use washers? What type of washers you use?
Yeah.
Bolts, typically they go from 1/2 inch to 1.5 inches. So anything smaller is not covered by the RCSC. So that's the range. The geometry is noted here as well. You can see what we are using in our connection is mostly 7/8 for the structural, for this end plate connection, and then for the connection to the beam. Different types of bolts, different grades. There's the A325, like I mentioned. This is the F182. This is the same thing, but this one's a twist-off bolt.
Yeah.
So I'll show you after this. We'll show you what I mean by a twist-off bolt. So A490, and then the A490 equivalent is F288. This is what we are using in this connection here, the F2280. This A325 is this connection, as well as the shear tap connection, and then the VRV plate connection. Okay, there are two types of bolts, type 1 and type 3. Type 3 is for weathering steel, so if you put it outside or anything like that. So typically we're using type 1. So type 3, when your bridge outdoor exposed to weather or anything, they use type 3 bolts. So corrosion resistant is better for this type, but since we don't have to worry about that, we're using type 1. Okay, and the nuts are DH. Again, same thing. DH3 is related to type 3. DH, they should be the DH1, but they don't. They just left it out before. So that's what we use.
Type 2.
They used to have a type 2. They got rid of it.
But the type 3 different. Type 2 is a corrosion.
Yeah, but now it's just limited to type 1 and type 3.
Yeah.
So there's no type 2 anymore.
Yeah.
They either condensed it or removed it. So type 1 or type 3. So type 3 is the weathering steel. Okay. That's the A325. Minimum tensile strength 120, 150. Okay. Maximum is 170. Pretension can be induced if we tire. Pretension can be induced when it's required. So you could pretension both of these both types. Differences between the 2 or 3 types of bolts is 807 is a common bolt. So you can see the tension is very low, but it's very ductile. The A325 capacity is higher, but again you're losing on some ductility. The higher strength, it's higher bolt capacity, but your elongation is lower. So when you're doing it, you can look at it as not as ductile, but not many times you will elongate it by 0.1 of an inch. So we're using this A490 and A325. The A307, we are using it, but only at the beam, the nailer connection on the top. The bolt, the wood to the steel beam top nailer.
The FY is about 65.
Yep, that's right. Yep. So this is lower FY. So loading of the bolt, you could load it in shear and tension or combined shear and tension. There's not many ways of doing it. So loading in tension means, we have a moment, you're pulling on the bolt, that's tension. Your loading in shear is when you're pulling the two, and shear splice is loading in shear. And this one is a combination where you have moment and shear is loading in that. Bolts and tension, the capacity is very easy, it's just Fu times AST. Okay. However, your forces are compared to it, and you must consider your prying action. So I'll get into prying action later. So for the AISC, they always put a phi factor, and then you do your nominal tensile strength. So this is nominal tensile strength, and then the area of the bolt, and there's a nominal area of the bolt. Okay. So why is the nominal tensile FNT? They actually remember the threads. They reduce the threads when you bolt the threads. So you have to subtract out the area from the thread.
Yeah.
Okay. And they're saying you could adjust the area by that amount, or you adjust the FU by this. So instead of adjusting the area of the bolt, they adjust the FU by 0.75. So the area you use is actually the true, like half an inch bolt, then use half an inch to calculate the area. You don't have to subtract out the thread, because they already took care of that in the FU number. So when they're calculating it, that's what some of these things come from. Prying action is when you're loading in something like that. Okay, so it's eccentric. You're introducing some sort of moment here. So the moment, then you have additional bolt force. Yep, then that's what prying. And it could be a high high axial load. So when we're checking our end plate here, prying is a concern, and we have to use that and include that in the calculation. We'll show you when we get to design an example where we're including that. Bolt and shear, you have a couple of them, slip critical or bearing. Bearing is just the bolt bearing into the bolt hole. Okay, slip critical is you're actually accounting for friction in the two planes.
Yeah.
So friction is between the two planes is accounted for, but what friction do you take? Okay, so here the differences between the two types, again, individual physical tests, long joints, uneven bolt. So in addition to your geometry, the bolt failure, let's say the mole, the longer the joints are, the stress distribution between the bolts are also different, and so you have to multiply the longer joints with some sort of factor to reduce their capacity. So for the bolts and shear, that's just the shear stress times the bolt. So that's what your shear deformation. In the AISC, how they're taking care of it is they publish a nominal shear strength, and you use the area of the bolt. Okay, so you don't have to do anything. You just multiply by a phi, which they give you. They give you the nominal shear strength, and depends on what bolt you choose, you calculate the bolt area. So again, if the joint is greater than 50 inches, then you reduce it by 20% based on what we just saw. Okay, reduce for bolts. The phi factor is for all cases is 0.75. So it doesn't matter what it is, they just conservatively use 0.75. Threads in the plane or not. So if you have a bolt, you have a threads. This is threads not in the plane. Okay, threads in the plane is when the threads go into the shear plane.
Yeah.
If this occurs, you have to take another 80% reduction because of the threads. So this one's outside, then you don't have to reduce the threads, and that's what the X and N are in this bolt. So go to the bolt section and show you guys what the right here. Yeah. So when you look at the shear capacity they publish, they have a thread condition N and then X. So when you exclude it, you get higher capacity, whereas not, you get lower capacity, and that's X threaded. And typically they say that's 80% difference. Yeah. Okay. Combined tension and shear. Well, actually, this is the tension and shear in that. They only show you one equation, but the Fn is this. It's different for if it's shear or tension. Okay, and then the bolt is the bolt area. So that's how they handle it and condense it in the C360 for the bolt design. Here we saw it once before, but that's where you get the tensile stress, and that's where you get the shear stress from for the bolts. So group A, group B. If you not exclude it, if you exclude it, so you get different numbers where you depends on the case. Okay. When we mentioned slip critical before, what is what effects are what parameters you have to look at when you calculate a slip critical joint. First of all, is what kind of friction or coefficient do you have? Do you design for? The first one is the coefficient, the slip coefficient. D is I believe is the some sort of ratio. Okay. The ratio installed bolt tension. Okay, so yeah, so typically when you specify a bolt free tension, the guys out in the field do it more because of the gun, so they know you always get higher free tension. So they give you 1.13 factor, so you could increase it. That's what that is. It's not one. They say, well, all the time install bolt tension to you specify is always higher. That's what they say, 1.3. Okay, phi is when you have no slip or effective load or a service load or effective load. So that's what a fee. But the HN, TB, and NS we'll talk about. NS is the number of slip plane.
Yeah.
TB is the clamping force, basically how much tension force you're clamping it down, or you're clamping it down to when your friction, don't do. HSC is another modification. Again, these are based on if your hole is the standard size, oversized, or slotted. They give you a number in the code. Okay, so T is for service preparation, because look at this one, is if you adjust it by a little bit, your whole strength is based on that. This one you can't change. This number you can't change.
Yeah.
This is the number of planes based on the geometry. This is based on the bolt. So the only thing you could you could do is to change the surface preparation, get a higher capacity, or change the bolt tension to get higher capacity. Okay. So here it is straight from the AISC 360, slip critical. Phi equals 1 when you have standard size hole. Oversized or a long slotted hole, your fees get smaller. Mu is the surface friction, the slip coefficient. Now that's based on what class of preparation you have. For us, we tested as a pretension for the production. One side is not painted, okay, but we're not counting on the slip critical. So we're not considering to be a slip critical. So if you do consider a slip critical, the preparation for the surfaces, there's some requirement for that. You have to blast it clean, or you have to make sure that you get to a certain friction. For us, we didn't test it that way, but we did have a pretension bolt. So ours, the only thing needed is pretension, and also we tested as regular steel condition. We didn't paint it or anything during testing. So we wanted to match the testing condition, which is like this. So we paint everything around except the area that's contacting the steel. We leave it because that's how we test it. Okay. If we test it, paint it next, then we might modify the arc of protection a little bit, and maybe modify the strength a little bit. But at this time, when you see the actual finished link, this side is not painted.
Also, when we paint it, well, what is it can affect to the strength?
When you paint it, this coefficient is going to increase or decrease.
Increase or decrease?
Yeah, we don't know because we didn't paint it, and depends on what preparation you might have. It's not paint; it's just prime. So it's not paint; it's prime. So we did not. They want us to match the test condition. Okay, a lot of these things, whatever you test it, we want to match exactly. So since we didn't do anything to it,
so we
just leave it.
This is not a slip critical.
We are not we're not concerned for slip critical on ours. So we don't have to check the slip critical for this portion. Mostly just bearing. Yeah, that's how we test it. It's odd, but yeah, we should be checking some of it, but no, we're not checking slip critical for the connection. When you combine both tension and shear, you have the 1.3, and the omega if you're doing a ASD level. Okay. Combined tension and shear, it's slip critical. We're not dealing with this one, so we won't have to worry about it. A lot of times when you're dealing with bolt connections, bolt bearing, so after all we talked about with just the capacity of the bolt, right? Now let's look at the capacity of the material itself when you're bearing into it. The first mode is use bearing on the plate. Okay, you could tear out the plate. Okay, so this dimension L sub C is critical, as well as FU and the plate thickness. So the bearing is based on basically this 3 parameter. So if you look at bearing in AISC, L sub C, T, and FU, these are the parameters that they have in here. So it's 1.2 at service low, 2.4 is the maximum. We are considering we're only using this one at service low. It's not my call, but it's that's what we say. We test it, and so we're going to use this one. It's very conservative for our design. So that's why when we're doing the design of the check, especially for other bolted connections, I'll go do that as well. This check where we're doing the bearing of the bolt, and as well the bolt, the shear tap when we're bearing, the one single bolt we're pulling on it. This it's gonna govern because thickness of the plate L sub C and FU. The only thing is these two parameters where we could control. FU is typically all the same for any material or the same grade. So we're using this equation for our check. When we get to that, I'll show you what that means. Another failure mode instead of the bolt hole bearing is the block shear. So you could see the block shear is you could fail in this way, and you could tear out the whole thing. But what they see is you always failure along the bottom first, then you tear out off the bolts. So you would have to basically consider both the shear plane, or the tension plane, and the shear plane. So this is tension plane and shear plane. So that's where the AISC comes in, where they consider tension fracture, tension plane, shear yielding in the shear plane, and that's where the block shear equation is. Okay, so the gross area in shear, and then the net area in tension. Okay, so these are the exact equations from the AISC 360. So plate yielding, tension. The tension mode is the same. You see these two? Okay, so tension fracture, and this is the yielding of the shear tap, the gross area, yielding of the shear tap, the net area. So they're checking both. So go back to this one. When this one it's failing, is always in tension. Okay, now you have to check, it's going to be along the bolt line or along the edge. So you have to, when you're checking shear, you have to check both the FU, A net, FY, A gross. You see the back, this term is the same for tension. So that's the block shear strength per AISC 316. Also, they have a UBS term. This one, if your stress is uniform, it's typically 1. If not, it's 0.5. Remember, we looked at this previously, very briefly, is in the shear lag factor that they have in here. But for our design, we're considered to be uniform. And then the UBS is 1 for our connection check. Okay, so those are basically the bolt capacity, and then the base metal capacity. So after the two, that's pretty much the strength of the bolted connection. However, now is when you're tightening it, the bolt, what kind of joint type do you have? Okay, and what kind of load transfer, and depends on, remember we say loading the bolt, you load it in shear only, you load it in tension, or you load it combined tension and shear. So for ours, this in here is tension, exactly. Okay, so what does it say? Static loading, snug tight. All loading, pre-tension. That means this bolt is pre-tension. Yeah. However, we don't want to have the framers have a tool to pre-tension it. So we test it as snug tight. Okay, that's the thing. If somebody points out, well, your load is tension only, but how come and then you're not static loading? You should be pre-tensioning, and that the thing is we test it to be snug tight. And that's one condition we put in the code. We tell you what are some of the exceptions in the bolting requirement. in 341, all bolts needs to be pretension. Okay, regardless of what. So for us, we put in that to be snap type. Okay, so that's tension. What about this one?
Shear.
That's mostly shear.
Shear.
Yeah. So shear, we have three options. Okay, shear resisted by shear, low by shear or bearing, resisted by shear bowing. Both pretensions require, but reasons other than slip critical. Okay, we fall under here. Okay, the reason is we did not prep our surface. Okay, the joint type still needs to be pretension. We need to pretension the joints. Okay, we don't prep the surface, so we're under this condition. Okay, so we are pretensioning it, but it's not a slip critical condition. So that's why when you look at the third one, shear low resisted by friction on fraying surface is required. We're not counting on that. We're not designing that for that. So our joint type is not slip critical, is pretension, and because of that, we don't need to prep the surface. So either way, so we are sticking with the pretension joint, but no surface preparation. Okay, so this is from the RCSC summary. So it's actually a pretty good one when you look at it. You can look at any conditions, and this tells you what joint type you have, what kind of preparation, and what section you should be installing your bolt, and how do you inspect it, and if you have any questions between the two, then what arbitration you use. Question?
How can we retention bolt? Retention.
I'll go through some of the methods later. That's the next.
And the shear type is the
snap type. Yeah, shear type is snap type. Okay, installation, bolt installation. So we have the snug type only and pretension. So how do you know if your bolt is pretension? There are many methods. In the RCSC, there's 4 methods to do it. Calibrated wrench, turn of the nut, and by tension control bolts or indicator washers. Okay, the calibrated wrench, essentially you want to measure the tension in your bolt. So the tool they use is calibrated and they measure it against. So every time you turn to a certain reading, then they know that's your pretension in the bolt. So that's the calibrated wrench method. The turn of the nut is, this one is proven in testing before. What they do is they typically turn their snap type and then they mark it, and then they want them to do additional quarter turn or 3/4 turn. When they do that, then they know they get the pretension. Okay, these two are easier to see and easier to visualize by the inspector. So for our OMF, we're using low indicator washer, the DTIs. For the SMF, on the top we're using tension control bolts. So that's how we get the pretension in the bolt. Okay, here is what the tension bolts look like and what they do to pretension it. So essentially, you have there is a tail here. When they turn it at a certain torque, after they reach the required torque and tension, and that tail basically twists off, shears off. So when somebody looks at it, okay, is the tail there? No, then that one is pretension. Okay, the direct tension indicators is, you see these bumps on top. Okay, when you tension the bolt, you're going to be compressing these bumps. So they have gauges where you can measure it. You basically poke it into this one. If the gauges will not go through, that means you have compressed it enough, then the bolt is tension. So that's another method of how to tell if your bolts are pretension. Ours, we actually use the OMF. We use the similar, but on the other side we have some orange stuff that if you compress it, it squirts out. It tells you. So there's another indication, visual indication. They don't have to, say, go up to on the ladder to measure it. Just an indicator. It's not, doesn't say it meets it, but it just tells them if they meet one and measure it, that one's okay. Then the pattern they can repeat everywhere else, that should be okay. So that's how you indicate tension in the bolt. Okay, review. Welded connection. I know 4 or 5 processes, and then there are certain ones that are pre-qualified in the AWS D141 to be used as in their welding procedures without having to do further testing. Welded joint types are CJP, PJP, and filler weld. Strength check is you have both to check the base metal and the weld metal. For the bolted connections, you have basically we have 2 grades: the A325, A490, or their equivalent twist off bolt types. There are types. You have the snug type, pre-tension, and the slip critical. So now you know what the difference between slip critical and pre-tension. Essentially, slip critical is pre-tension with some surface preparation. Yeah. Bolt limit states, you have tension, shear, or tension plus shear. And then material limit states, you have bearing and block shear that we talk about. So we have the 2 essentially limit states. Okay, that's it. So this one is connection design, and we'll be applying all these to our connection design tomorrow. So I'm actually going to be covering all these again in when we're doing our connection design, which methods or which limit states we check, and what kind of what kind of weld type do we use, and what's our bolt grade, and then joint type and all that stuff to our actual connection. Anything else?